Did you know what just happened? That's what we call plant growth. One of the main factors for plant growth is auxin. Auxins play a key role in promoting cell elongation, particularly in the stem and coleoptiles. This effect is essential for the overall growth and development of C3 plants, influencing the length and structure of stems, leaves, and other plant organs. Auxins stimulate the activation of enzymes, known as expansins. Expansins play a crucial role in loosening the cell wall by disrupting the hydrogen bonds between cellulose microfibrils. This enzymatic action allows the cell wall to become more flexible, enabling cell expansion. Auxin promotes the uptake of water into the elongating cells. This increased water content creates turgor pressure within the cell, similar to inflating a balloon. Then, pH in the cell wall decreases through the activation of proton pumps. This acidification, known as the acid growth hypothesis, activates enzymes that modify the cell wall components, microtubules, structural components, and influence the direction of cell elongation aligned by Auxin providing a cytoskeletal framework that guides the elongation process. Next, specific genes expression help by Auxin encode proteins that are crucial for elongation process, such as water.
In the lush landscape of plant growth, apical dominance is the clandestine choreographer orchestrating the dance of nature. But before we enter this captivating realm, let's set the stage by uncovering the fundamental characters in our botanical drama. To commence our discourse, let us scrutinize the foundational architecture of a plant. It comprises two principal entities: the apical shoot, standing as the primary vertical axis, and the lateral bud. Allow me to introduce auxin, a pivotal plant hormone localized at the apical shoot zenith. Its function is paramount, stimulating growth and elongation of the apical shoot, thereby dictating vertical ascension. Of particular interest is the phenomenon of apical dominance. Auxin, in addition to its growth-promoting role, serves as a signaling agent, inhibiting lateral bud growth and orchestrating a hierarchical development. Conceptualize, if you will, the removal of the apical shoot, the plant's leading force. Deprived of auxin's regulatory influence, lateral buds, in turn, experience unhindered elongation and increased prominence. Let us introduce an additional actor in this botanical drama. Cytokinin. Synthesized in the root, this hormone traverses the plant, accumulating in the apical shoot and bolstering its growth in synergy with auxin. Upon the removal of the apical shoot, a consequential absence of auxin allows for the unimpeded distribution of organic compounds and cytokinin to lateral buds, culminating in their elongation.
A plant will develop if it receives adequate water, minerals, and energy, right? Well, sort of. However, there are other factors to consider, such as why plants grow in the direction of light, rather than straight forward, and why the roots develop below, while the stem grows upward. It is not like the plants have eyes or to tell where the sun is. Yet, given that it was created in the tips of the stems and roots, how does it really accomplish this? Diffusion transports auxin throughout the plant's stem and into every area of the plant. The cell's flexibility changes as a result of the auxin. Longer growing and more water-absorbing cells are more elastic. Strangely though, stems and roots respond differently to high concentrations of auxin. Whilst the stem cells grow more, the root cells actually grow less. So, auxin makes plant grow. The reason for the bending is that the auxin on one side of the stem is broken down by more light hitting that side of the stem. Consequently, growth slows down on the light side, and shoots and leaves turn toward the lights as a result of the darker side's faster growth, which is ideal for the plants for photosynthesis. The tips of developing shoots produce auxin. If the tips are severed, auxins cannot be generated, which prevents plant growth. If the tips are covered, however, auxins can still be created. Light cannot degrade them, and tropism cannot continue. The plant does not bend toward the light, instead it grows straight up. Auxins affect root cells in the opposite way. Auxins reduce the amount of growth in roots. Roots that are shaded develop slower because they contain more auxin on that side. As a result, the root's bright side can spread farther and bend away from the light. And as if that wasn't strange enough, auxins to gravity are also having an opposite effect. The bottom side of a horizontal pathway grows less and has higher auxin content. Positive geotropism results from the roots bending downward in the direction of gravity. Naturally, though, the stem reacts differently. In a horizontal stem, for example, the bottom side has more auxins due to less direct solar exposure. However, auxins stimulated stem growth, which made the bottom side of the stem grow more and bent the stem upward against gravity, resulting in negative geotropism.
Next is root initiation. Auxin is a key plant hormone that plays a crucial role in various aspects of plant growth and development. It is including root initiation and the formation of lateral roots. The tips of root contain apical meristems, regions with actively dividing cells. Auxin is synthesized in the apical meristem. The accumulation of auxin creates concentration gradient and stimulates cell division and elongation in the root cells. A lateral root primordium is formed as a result of increased cell division. The lateral root continues to grow and elongate, eventually emerging through the outer tissues of the main root.
Ever wonder why leaves fall? Leaf abscission is simply when a plant drops its leaves. The process of leaf abscission includes many physical and biochemical changes, which are majorly regulated by the plant hormones. Leaf abscission can be divided into 3 phases: leaf maintenance, shedding induction, and shedding phase. The first one is leaf maintenance. Auxin gradient proceeds from the leaf blade to the stem. Cells of the abscission zone stay unchanged as auxin inhibits leaf abscission. Next is the shedding induction phase. During this phase, the Auxin gradient is either reversed or reduced. It occurs normally during senescence, and cells in the abscission zone are now more sensitive to ethylene. Lastly, the shedding phase. In this phase, cells react to the low presence of ethylene. This stimulates the gene to encode for hydrolytic enzyme to be induced. This enzyme will break down cell wall of the cells in the abscission zone, resulting in the shedding of the leaves from the abscission zone.